All right. So I wanted to just, I felt like our discussion of optical rotation was somewhat confusing. This is an issue that, you don't need to know how it works to understand it. On the other hand, if you've ever been confused about why chiral molecules can do this, that is, rotate plane polarized light, it may be worth talking about. As we mentioned, if you look at the this is the direction of propagation of an electromagnetic wave. The electric field and the magnetic field propagate in orthogonal directions. And normally, light that comes from just regular sources is not polarized, and so you have many different photons superimposed on each other that are oscillating in sort of all possible directions. Each photon oscillating in a certain direction, but all of them not having the same direction of oscillation. You pass them through a polarizing filter, and anybody that's not oscillating in the correct direction gets filtered out, which is why if you look through polarizing filters, they're a little bit dimmer than just the regular light. This is why when I went to see The Last Jedi in 3D, the 3D effects were interesting, but the light was dimmer, so I couldn't tell, for example, that Laura Dern's character had purple hair. It looked vaguely tinted, but I didn't know. And so anyway, so I don't recommend seeing movies in 3D because it's too dim. But it's dim because the polarizing filters filter out some of the light. Now, why should chiral molecules rotate plane polarized light? Well, this is a bit of a stretch, but mathematically you can represent plane polarized light as a one-to-one mixture of circularly polarized light in the left and the right-hand direction. So what do we mean by this? So here's a GIF of two different handednesses of circularly polarized light. The direction of propagation is this way, and we're looking at it from behind. So from behind, we would say this is clockwise, right-handed circularly polarized light. And what we mean by that is the direction of oscillation is spinning around in a circle. It traces out sort of a helical pathway. And then you've got left-handed circularly polarized light, which is tracing out a pathway in a counterclockwise direction. And you remember we talked about axial or helical chirality, where if you look down a molecule, remember we talked about allenes and we talked about M and P versus chirality. Anyway, helices are chiral, and so you can think of circularly polarized light, the right and left-handedness, as being two enantiomers of light that together make a racemic mixture. So how does it work that you can theoretically decompose plane polarized light into two equal amounts of circularly polarized light? So I've tried to illustrate that here. Here is the circle just shows us, I don't know what the circle shows us. We're looking down the direction of propagation of the wave. The size of the arrows tells you the magnitude of the electric field at this particular point in time. On the right, you've got plane polarized light, and with, what the heck is going on here? With increasing time, that vector decreases in magnitude, goes through zero, and then points downward, and then it's going to go back up. So it's continually oscillating. We're basically looking down this axis as a function of time and watching the arrow get bigger and then smaller and going negative. So at time zero, the left-handed and right-handed, or clockwise and counterclockwise circularly polarized light, except I got clockwise and counterclockwise mixed up, didn't I? Man. I always get right and left-handed wrong the first try. You are witnesses of that. So at time zero, we'll say both counterclockwise and clockwise are pointing in the same direction. At time point 1, they've both moved, they both rotated through an angle, but equal angle in opposite directions. If you zoom in on that and look at those two vectors, if you remember from math or physics, you can always deconvolute a vector into orthogonal components, one in the x direction, one in the y direction. And if you think about adding these two vectors together, their x components are going to cancel each other out. One's in the positive direction, one's in the negative direction. Their y components are going to reinforce each other, but together they're not going to add up to as much as this because some of them has been in the x direction and canceled out. So the sum of these two vectors is still in this upwards direction, but smaller in magnitude. I think I'm totally butchering that as I explain it to you. So do you want to ask me any clarifying questions? Yeah, go ahead.
So with this, this isn't as much about the math and vectors, but does your sample have to be in crystal form for this to work? Or
no, the sample doesn't have to be in crystal form to work. It just typically for optical rotation experiments, you have it in solution at a certain concentration.
So it doesn't matter what angle the light's hitting your molecule.
No.
It'll always do it the same way.
Well, so what happens in a chiral sample is for optical rotation experiments, what changes when the sample is chiral is the index of refraction for counterclockwise light is different from clockwise light. Index of refraction is related to how fast light travels through that medium. So your text says, okay, suppose that left-handed light moves faster through the medium than right-handed light. When they recombine at the end, they're going to be out of phase with each other because one's moved faster than the other. And that's going to lead their x components to be out of sync with each other. And so overall, you're going to observe in the end that the plane of rotation has rotated, the plane of polarization has rotated. It's a little tricky to see how that would be. In order to envision it, what we would have to do is say, okay, what if after we went through the chiral sample, dang it, really small eraser. What if after we went, what if the clockwise light propagates really, really fast so that when we're analyzing it, the vector has moved to that point. Now the x component in purple is way bigger than the x component in orange. And so if you were to add those two vectors together now, probably we're now somewhere like this, intermediate between the two. So so this is when the angle of rotation for one-handedness of light is different from the angle of the other-handedness of light. And so overall, that tilts your polarization over. Yeah, Dakota.
So it looks like if the vectors rotate at different rates, you're going to end up with circularly polarized light in a different...
Oh, yeah, I suppose. If the vectors are rotating at different rates, then perhaps your plane of polarization actually rotates. Yeah, I think that's the case, though I don't know that it's the frequency of oscillation hasn't changed, just the speed, I think, through the medium. I could be wrong on that, and I really don't understand the physics, so I'm sorry. But simply, I mean, if you think about it at the level of, polarized light is a racemic mixture of clockwise and counterclockwise light, and therefore a chiral molecule will interact differently with counterclockwise versus clockwise light. That's basically enough to understand the origins of the process. So we've talked about how optical rotation works. Your text mentions circular dichroism. Optical rotation is about differing index of refraction of circularly polarized light, left and right-handed. Circular dichroism is about differential absorption of clockwise versus counterclockwise light. And this is a technique that can be used. You can get a characteristic circular dichroism spectrum of a chiral molecule, and sometimes people do that, especially with chiral molecules that absorb in the visible and or UV regions of the spectrum. This is especially useful for people studying protein structure. So here I'm showing you a crystal structure of an alpha helical bundle, trimeric bundle of helices. And of course, now we've got the crystal structure, we know what the structure is, but even without the crystal structure, there are some characteristic patterns in a circular dichroism spectrum that can tell you something about the secondary structure of your protein. So here is a graph of CD data obtained from my lab. Here is wavelength on the x-axis. On the y-axis is a term called molar ellipticity in unintelligible units, and but it's related to the differential absorption of left versus right-handed circularly polarized light. A helical protein, an alpha helical protein, will tend to show a minimum in the CD spectrum at around 222 nanometers and again at 208 nanometers. And if you take the ratio of the peaks at 208 and 222, you can get an idea as to whether those helices are associated with each other or are on their own, and the spectrum changes. You can also turn up the temperature and monitor at that wavelength, and you get what's called a thermal denaturation curve, and you can fit those data to calculate how what the change in free energy is as the protein folds versus unfolds. So this is a very useful technique. When I was here, I took 468, which was then the biophysical chemistry course. I'm not sure what it's called now. And we spent a while talking about circular dichroism, and I swore up and down that it was the most useless thing I had ever heard and that I would never use it, and it's now mostly all I do. So, famous last words. Okay. Want to talk now. Any questions about that? Anything you want to talk about? No? Okay. To use the CD instruments over in life sciences, and you have to have a certain kind of quartz cuvette, you might imagine that because this is a technique that's sensitive to polarization, you don't want your cuvette to have any defects that might itself impact the polarization of the light that you're passing through the sample. So these are very tiny cuvettes, 1 millimeter path length. If you've ever broken something in your lab, it's probably not as bad as what I'm going to tell you now. There's a student who's no longer here, and Kim, I don't think you ever met this person. Did you ever meet Sam? No. Okay, yeah, way before your time. He was heading down to the CD instrument, which was then in the Widsoe building, also way before all of your guys' time. And he was holding a bag, a little plastic bag full of 5 of these cuvettes, each of which is probably worth $500. And he's standing there talking to a lab mate and just accidentally, I don't know how this happened. I don't know how you're standing there and talking and then let go of something. I can't complain because I myself am clumsy, but yeah, he dropped the little bag of cuvettes and it shattered. And the problem, they weren't even our cuvettes, we were borrowing them, so it was very sad. And he was embarrassed and sad, and I was angry for a while, and then I felt dumb about being angry because I myself am a klutz. So anyway, likely if you've broken something, you haven't done it to the tune of $2,500. So
This is why we have the phone holder.
this, yes, we have.
That's now.
That's right. We have graduated to a system where you never carry the cuvettes in a little bag again. And we have a foam holder so that if you drop them, they will be able to recover. Anyway. Want to talk now about a couple of tools that can help you identify chiral molecules and chiral environments. So this will be a little bit, we've talked a little bit about symmetry operations before. We're going to talk a little bit about them now. If any of you are in 514, probably you know way more than me about this. I know next to nothing about point groups, but fortunately we only need to talk about two different kinds of rotations. Proper rotations and improper rotations. So proper rotations I envision as some sort of posh British kind of accent speaking in the received pronunciation of the BBC and the royal family. Improper you can think of as sort of the local dialect, perhaps some badly affected Cockney accent from a United States actor trying to sound British or something like that. Proper rotations are just rotations about an axis by 360 degrees divided by n, where n is an integer, that leaves the molecule unchanged. All right, so an example of a proper rotation would be this molecule. We would put a rotational axis right down into the page along that perpendicular to the page at that point. We'd rotate it by 180 degrees, and boom, we've got the exact same thing. We would say that this molecule has a C2 axis of rotation, because 360 divided by 180 is C2. So the molecule is C2 symmetric. You may be interested to know that molecules that are that have C2 symmetry are generally chiral. So molecule is chiral. And there's tons of examples in organic chemistry of C2 symmetric ligands or catalysts that are chiral and induce favor one enantiomer over another in a reaction. Yeah, go ahead, Dakota.
Are you talking about just C2 or C2H or V? Because water has a C2 axis.
Right. So I guess I don't mean that all molecules with C2 axes are chiral. I guess I mean that if that's the major thing, and this is where I'm bad at point groups, I don't know.
Yeah, I think I remember reading that having S operations is what makes sense.
Right, and we're going to talk about that. So I guess, yeah, if you can find a C2 axis, it might be chiral. If you can find an improper rotation axis, it's definitely not chiral. So
C1 molecules tend to be chiral.
that's right. If there's no rotational axis at all, that they do tend to be chiral. And there's some point group theory stuff that you can get into, but that we won't really need in this class. Improper rotations are, again, you're going to rotate around an axis by 360 degrees over n, where n is an integer, followed by reflection through a mirror plane, but not just any mirror plane, one that is perpendicular to or orthogonal to the rotation axis. And if a molecule has an improper rotation, that means if you do this process, it leaves the molecule unchanged. All right, so allow me to give you an example of that. The following molecule has an improper axis of rotation. It's an S2 type symmetry. You put the axis, again, perpendicular to the page, going down into the page at the indicated point, and you rotate by 180 degrees. And if you did this, you would say, hold on, this molecule is not C2 symmetric, and I would tell you exactly, but we're not done yet with the symmetry operation. So then we have to take a mirror plane, except it's not just any mirror plane. It has to be a mirror plane that is perpendicular to the axis. So the plane that is perpendicular to our axis of rotation is the plane of the page. So now we have to reflect back into the page. So this is where you're going to have to stretch your brain. It took me a minute. If we're drawing the reflection that's below the page of our molecule that's on top of the page, we would see, whereas above the page, the OH group on carbon 2 is pointing down towards the page. In the reflection, that OH group is going to need to be pointing back up towards the page. And similarly, we would find that stereochemistry for carbon 3. Oh, look, it's the same thing. So this has a improper S2 type symmetry, and therefore it is not chiral. You can also say achiral, though people get confused when you say this is a chiral molecule versus this is an achiral molecule anyway. So just be clear. And in general, chiral molecules overall will lack improper rotation axes. If your axis is S1, that's 360-degree rotation, so turn around all the way and then reflect through a mirror. That's just mirror plane symmetry, or we'll sometimes call that sigma. By the way, if you change the shape of this molecule, it becomes even clearer that it's not chiral. This is just a meso compound, which also has an S1 axis. You rotate 360 degrees and then reflect through a plane, and you got the same thing. So this can be a way, if you're identifying symmetry elements in a molecule, it can be a way to sort of tell you whether or not things can be chiral. Again, I'm not sure I explained that. Any questions, clarifying questions you want to ask? So where this is really useful is deciding whether groups are equal or not in molecules, and whether various groups should have, say, the same chemical shift or the same properties or not. So we're going to introduce a term that you likely have heard before if you've taken the organic lab, and that is homo versus heterotopicity. So a homotopic group is any group that is interconvertible. Two groups are homotopic if they're interconvertible by a CN axis of the molecule. And groups that are homotopic are always equivalent, even in a chiral environment. So examples of homotopic groups include HA and HB in propane. If you put an axis here and make it a C2 axis, you'd be able to see that protons HA and HB exchange positions. HA and HB are fully equivalent under all circumstances, even in a chiral environment. Yeah?
So homotopic groups can be on different carbons. There's an axis between them.
That's right. So here's an example of that. Dun, dun, dun. Here is a molecule that is chiral. And this molecule likewise has an axis of symmetry, a C2 axis, rotate 180 degrees. These two methyl groups are homotopic. These two phenyl groups are homotopic. The two oxygens, oops, I wanted a different color than pink. The two oxygens are homotopic. And those two carbons there are homotopic. Okay, so this would be useful in an NMR spectrum of that molecule. Do you expect to see two different phenyl groups? No, you don't, because they're equivalent, symmetry equivalent. They have to be the same. Note that this molecule is chiral. Nonetheless, those two methyl groups are equivalent. So you may be used to the idea that, oh, if you have a CH2 group in a chiral molecule, those two protons are diastereotopic. Beware, not always. If you can exchange them by a C2 axis, then they are always equivalent. Yeah?
And do you have to be able to exchange all the groups as well? For example, if we put an OH instead of a CH3 on top, would they still be?
Well, so the whole molecule has to have that symmetry. That's why we do symmetry axis of the molecule, right? So if we suddenly change this to, I don't know, I'm trying to make stuff up, but on the fly I'm not doing it very well. If we change this to a methyl group, we break the symmetry. That C2 axis no longer exists, and then those methyl groups are equivalent. All right. We can also talk about homotopicity when it comes to trigonal planar carbons. So here is a ketone, and we can talk about whether the top face or the bottom face of the ketone are the same. Top face, bottom face. In this case, we have a C2 axis of symmetry that can convert the faces into each other. What used to be the top face can become the bottom face. So these are what we will call homotopic faces. And this has a consequence for reactivity. If you were to take this ketone and react it in a, say, lithium aluminum hydride reduction reaction, and react via the top face or the bottom face, you're going to end up with exactly the same product. The products are not going to be isomers, they're going to be, your text uses homomers, which sounds kind of silly because that just means same thing. All right. So when you react from two homotopic faces, you get the same product. Now, that's probably obvious to all of you. So, yay. But it will be useful as we start to talk about groups with other topicity. So, and this is something I really have never understood. In my experience, undergrad textbooks do a cruddy job. They'll tell you about enantiotopic and diastereotopic, but they'll do it through some strange thought experiment, and then they won't tell you why it matters. So this is like the first time in my life I've understood what enantiotopic means and why it's useful. Enantiotopic groups are, and this is why we learned about symmetry operations. Enantiotopic groups are interconvertible by improper rotation axes of the molecule. And this can be a mirror plane, or this can be some other improper axis of rotation. They are, like homotopic groups, they are that's funny, equivalent, except in a chiral environment. All right, so as an example, let's look at a CH2 group in a not chiral molecule, HA and HB. They are interchangeable not by a regular axis of rotation, but they are interchangeable by either the S1 axis, where you rotate 360 degrees and then reflect, or you can just think of it as a mirror plane. The mirror plane causes HB and HA to be identical to each other. You see that? One is just the reflection of the other if our mirror plane is the page. These are enantiotopic, meaning they're going to be equal to each other unless you're in a chiral environment. And to see that that's true, just sort of imagine putting your hand underneath this molecule and forcing the chloro to be near your pinky and the methyl to be near your thumb. Then the two protons are different, right? HA would be down on the palm of your hand and HB would be pointing up outward. Your hand is chiral. It can distinguish between those two protons. And we're going to have a way of talking about the difference between these two protons. We're going to call, so they are equivalent except in a chiral environment. And to indicate that, we're going to do the following. We're going to imagine that, for example, HB is heavier than HA. And then we'll say, okay, priority 1, priority 2, priority 3, going from 1 to 2 to 2 to 3, then 3 back to 1. That's a clockwise rotation. This molecule is not chiral, and the carbon that we're talking about is not a stereocenter. But if we replaced HB with something that was not a proton, it would be a stereocenter, and we're going to call this a pro-R proton. Okay. Now, just because it's the pro-R proton doesn't mean if we put a group there, the stereocenter is going to be R, because of course it's going to depend on the identity of the group and what the priorities are. Yeah.
How's this any different from the deuterium test? Or is this?
Yes, this is the deuterium test. Yeah. So by the star, I mean, let's imagine that, for example, that were deuterium. Yeah. So what Kim is describing, I was trying to abbreviate through, but to do the thought experiment, you say, okay, well, what if we replaced proton B with deuterium? Then this would be a stereocenter and it would be R. So we're going to call proton B the pro-R proton. Similarly, we're going to call this the pro-S proton. Why do we bother with that? Well, if you study enzyme reaction mechanisms, enzymes are chiral, and you can show through various experiments that an enzyme will remove the pro-S proton instead of the pro-R proton, depending on the situation. You can do this with groups that are not protons. So as an example, here are some enantiotopic chloro groups. And you know what? I'm going to just make this easier on us. Put CH3 in the back, put chloro there. If we pretend that this chloro is a heavier isotope, then we would go 1, 2, and 3, and then that would be the pro-R chloro. Whereas if we made this chloro the heavier isotope, oops, I'm going crazy. 3, 1, 2, 3. That's counterclockwise. We would call this the pro-S chloro group. All right, pro-R, pro-S. Any questions about that? Yeah.
If we go going back to the first example again with HB.
Uh-huh.
So we're saying that if we substitute the HB with something else, it will be R? Because
So the experiment you do is you substitute HB with something that's a proton but heavier, like deuterium. That way you don't change the priority relationships at all.
yeah, I was thinking like, what if we put a butyl group?
That's right. Yeah, you could screw this up if you put something else there. And that's why I'm saying that just because a proton is pro-R doesn't mean if you do a reaction and put something there, the stereocenter is going to be R. If it were deuterium, it would be, but all bets are off if it's something bigger.
Okay.
But what this is meant to say is that a chiral environment can tell the difference between the pro-R and the pro-S protons.
So if that's chiral there, the molecule on the bottom,
Yeah.
does that mean that we can tell enantiotopic protons will give different signals in partially deuterated solvents?
No, what that means is that enantiotopic protons will be identical and give identical chemical shifts unless you put them in a chiral environment. And there's I think on page 308 in the text, they show you an example of a chiral shift reagent, which is a chiral metal complex that coordinates a molecule, and then you can see the difference between enantiotopic. Yeah.
So what you're saying is if you stick something in a chiral solvent, you can then see the difference between enantiotopic hydrogen.
I suppose if you wanted to spend lots of money on a chiral solvent, a chiral deuterated solvent, then yes, you could tell the difference between enantiotopic protons. All right? Yeah.
I'm trying to think this through. It would be harder because even if we took chloroform and deuterated one atom, we would need to add tritium maybe to the other to get it to be chiral.
Right. Yeah. So, for example, you would probably you would say that the in this molecule the methyl groups are the protons on the methyl group are homotopic, because if you replace one with deuterium, they're still equivalent. Yeah. All right. We can talk about, similarly as we did for ketones above that had homotopic faces, we can talk about enantiotopic faces of ketones. So here is an example of a ketone that lacks a C2 axis but does have a mirror plane. In this case, the mirror plane is the one in which each atom that's attached to the carbonyl carbon resides. It's the plane of the ketone. You have a top face and a bottom face, and those faces are enantiotopic. Enantiotopic, yep. And we're actually going to have a name for one face versus the other. To do this, we simply assign priority 1, 2, 3. And from the top, going from 1 to 2 to 3 would be, it looks like counterclockwise. So the top face is, we're going to call it the psi face. Psi is, I think, the first two letters of the word that the designation S comes from, sinistral or something like that. Similarly, if we look on the bottom, going from from our perspective on the bottom, going from 1 to 2 to 2 to 3, 3 back to 1 would be clockwise. You have to sort of lean back, put yourself under that thing, and then go 1 to 2 to 3. Okay, that's clockwise. And so we're going to call that the ray face. These faces are enantiotopic. Why do we care about that? First, if you react from either face, you're going to get, in this case, enantiomers, right? So if we react from, if we do our lithium aluminum hydride reduction from the psi face, we'll get the following enantiomer. it okay if I just write an ethyl group like that? Are you guys cool with that? And then if we react from the Ray face, you know, maybe it doesn't come from the Latin. Maybe somebody was just a fan of is it Italian names for notes? Do, re, mi. Is C a note in Italian, or is it T? T? Okay. Well, probably depends. Okay. So there you are. Here you've got enantiomers. Now again, the enantiomers have the same chemical and physical properties. So you would predict that in the absence of a chiral reagent, the transition states leading to these products should also be enantiomeric, would have to be the same energy. So the rates of reaction for either enantiomer has to be the same. The relative ratio of one enantiomer for the other has to be 1:1. Okay? So identifying that this ketone has enantiotopic faces leads you to say, okay, if I react from the top face versus the bottom face, I get enantiomers. Now, we did that in 351 and 352 without calling it this. We would say, oh, this molecule is flat and the one face is the same as the other, and therefore, but it's useful to recognize the difference between the ketone I've shown you here that has enantiotopic faces and the ketone above that has homotopic faces. If you do the reaction with the ketone with homotopic faces, you get the same product. If you do it with the enantiotopic faces, the ketone with enantiotopic faces, you get enantiomers. And again, a chiral molecule or a chiral reagent or a protein can tell the difference between the psi and the ray face of a ketone. All right. Anything more we need to say there? The last thing we'll talk about in terms of topicity is diastereotopic groups, and these are groups that cannot be interconverted by a symmetry operation and are therefore always different. Now, we're going to make a distinction between they have to be different versus how different are they actually. For example, two groups that are diastereotopic theoretically should have different chemical shifts, but the chemical shifts might be so close as to make it difficult to see the difference between the two. Let me give you an example of some diastereotopic groups. So in this chiral alcohol, HA and HB are diastereotopic. They cannot be interconverted by any symmetry operation at all. And again, with ketones, let's just imagine the following ketone where one of the alpha carbons is a stereocenter. The top face and the bottom face are different. So we'll call these diastereotopic faces. And again, if you reacted this molecule from the top face with lithium aluminum hydride, you would get, the products that you get from top face versus bottom face reactivity are going to be diastereomers now instead of enantiomers. Okay, these are diastereomers. You see how that's the case? The stereocenter of the alpha carbon hasn't changed, but we've got both configurations at what used to be the carbonyl carbon. Because these are diastereomers, they are always different, and the transition states leading to them are also diastereomeric and may be different energies. And so one of these can form faster than the other, and in the final product, you could have a non-50-50 ratio. They don't have to be 50-50. They are different, and it's never going to be exactly 50-50. Now, your text points out that there may not be a huge energy difference in the transition state between the two diastereomeric transition states. There may also not be a huge energy difference between the stability of the products. So your ratio might accidentally be close to 50-50, but it doesn't have to be. All right? So why is this important? Controlling reaction stereochemistry is an important part of synthetic organic chemistry. And this sort of talking about these issues sort of lets you know what the key strategies are going to be. If you want to do what's called asymmetric induction, that is, if you want to tell if you want to do a reaction that favors one enantiomer over the other, and your product and your starting material is not chiral, you want to distinguish between two enantiotopic groups, you're going to have to use a chiral reagent, right? So there are examples of this, and this is these are the reactions that are considered to be most useful. These are reactions where you have a chiral catalyst that creates, now because the catalyst is chiral, a reaction with one enantiotopic group versus the other is now an issue of diastereomers. And so the chiral catalyst can distinguish between the two. Alternatively, if your molecule already has a stereocenter, maybe you don't need to use a chiral catalyst because your diastereotopic groups are different and don't have to react the same. So in many cases, if you start with something that's already chiral, you can take advantage of what's called diastereoselectivity to get one product versus the other. Another strategy is if you have a molecule where protons are enantiotopic, if you can functionalize that molecule temporarily with a chiral auxiliary, you now turn them into diastereotopic protons. So if you've learned about the Evans asymmetric aldol reaction, that, and a lot of reactions have to do with you add a chiral auxiliary to now convert enantiotopic protons into diastereotopic ones, and then you can tell the difference. Yikes. All right, what else? The rest of chapter 6, I'm trying to think, we are going to talk about the difference next time between stereospecific and stereoselective. Chapter 6 delves into chirality and stereochemistry of knots and supramolecular structures, which is interesting, but I think probably beyond the scope of what we need to talk about. If at any point in your future you're going to be making molecules that twist around and make loops through themselves, you should look at this chapter because it'll give you an idea of what the stereochemical issues are. If you're going to be making supramolecular devices, there are some stereochemical issues there that you might want to look at. In my opinion, unless you're really interested in that area, it's probably not worth actually discussing in class, so we'll skip over that. So next time we'll finish up on stereospecific versus stereoselective, and then we'll move on to chapter 7, which is, I think, kinetics, which should be scary for you and for me because I don't know a lot about it. All right, we'll see you next time. That's a ringing endorsement, right? When the professor